Hey, Samuel, are you there? Oh, I can't hear you yet. Give me a moment.
Oh, sorry. No, it's on my end. I just have a mute on my headphones.
All right, not a problem. Well, how are
Yeah.
you doing today?
I'm doing good. Thank you.
Good, good. Well, tell me about the studying. How's that coming along for you?
It's going pretty well.
Okay,
Yeah.
have you made any progress? Anything new there? Or
Well, no, I feel like that lesson last week. I feel like it's just stuff that I've went over in class. So I don't think it was yeah, I didn't find any problems with it
good,
necessarily.
good. Well, sometimes it's good to have a nice refresher
Yeah.
as we're moving forward with the stuff.
Yeah. Definitely.
Now, I want to do is come over here to the bit paper
Yep. But
and
could you screen share again? Because it doesn't really, it's like unreliable on my end.
can you see that right there?
Uh, are you screen sharing?
I most certainly am.
Oh,
See,
okay, yeah, now
can you
I
see it
see it.
now?
Yeah.
Okay. Now, let's take a look at number 20 right here. This is what we are talking about last time was logarithmic differentiation and implicit differentiation. And recall, when's a good time to use logarithmic differentiation? When would you want to use it?
You probably want to use it when there's a lot of like a rigorous application of the product quotient rule, whatever.
Right. When you have a lot of products, a lot of quotients, that's usually a good time to go ahead and do that. And when would be a good time to start doing like implicit differentiation? When do you use that?
Implicit. Well, when there's just x and y and stuff.
Okay. Now, what's the difference between something that's implicit and something that is explicit? What's the difference between those two?
So, you have to derive why more. I'm not sure.
Well, if I say something is explicitly stated versus something that is implicitly stated, what's the difference there?
Explicitly, it's like, oh, implicit is like an assumed thing. Explicit is like, it's like something that's like specifically that thing
Mhm.
is yeah.
Okay, so it's like it's implied. So it's y is a function in terms of x, but it's not all spelled out.
Yeah.
Or maybe some kind of curve and it's not all spelled out. So you have to kind of look a little deeper and really look between the lines, so to say, to be implicit. You're implying something.
Yeah.
Now, Samuel, can you take number 20 here and can you find me y prime?
Y prime. Okay, hold on. I'm just gonna use the annotate. I don't know if you can see it. Well, it's not gonna be like a thing. It's just gonna be in terms of. Wait, would A be a constant?
Yes, a would be a constant here.
Okay. Oh wait, so it'd just be zero then. Wait, wait, negative. wouldn't just be y equals negative x?
Okay. Now, you did something wrong up here. Can you see what you did wrong? What did you
Uh,
miss?
is something wrong?
Mhm. When you're doing something implicitly, what's the
Oh yeah,
one
oh
thing you got to
yeah,
watch out for?
oh yeah. I forgot. I forgot. Completely forgot. Sorry.
You forgot the y prime
Yeah.
right there. So every time you encounter the y, taking your terms of x, or y's you're considering like being a function in terms of x, make sure you
Yeah.
tap on your y prime. Remember what y prime means? It's something like dy dx.
Yeah.
So if you have like something like x prime, it's like saying dx, which is one.
Yeah.
That's why you don't worry about it. But we do need
Yeah.
to worry about it when you have the y prime.
Yeah.
Okay, so let me if you
Yeah.
can go and erase that annotate, let's try it again.
Yeah. Okay. Yeah. Yeah. I'm sorry. So
Okay, try it one more time.
okay, I'm just gonna do that. So this.
Okay, so let's just kind of make sure you got it okay. You said 2/3 x to the negative 1/3,
Yeah.
and then 2/3 y to the negative 1/3 y prime equals
Yeah.
0.
Yeah.
And then you just kind of move things around.
Yeah.
So let me see if I can move this up a little bit. You subtract it to the other side. Now you can keep it as a negative exponent, or you can drop it down and make it a positive exponent. And it's usually a good idea to keep things positive in math and in real life.
Yeah.
And here's your y prime now.
All right.
So you multiply both sides. That's where the negative came into focus. This is where you got your x to the 1/3. You multiply it through, you got it.
Yeah.
So there it is. Now, let me give you another problem. Let's take it to the next level. Can you find the second derivative for this equation? Now,
Secondary.
if you
Oh.
can make your screen a little bit bigger there, Samuel, you're going to need a little bit more room.
Uh. How do I? Oh. Oh yeah. Okay. Um. So okay, I got it. Annotate. Shoot. Wait. What did I do?
Hold the control button, hit the minus. You're going to have to zoom out in your browser. Or can you see it
Uh,
okay on my side?
oh, I'm on annotate because
Oh,
I
that's right.
um
All right, we'll take it from there.
yeah. Hold on. I accidentally hit my video panel or something. It's like okay, there we go.
Okay, so you're looking at 3x
I got it.
squared minus 2y squared equals 5.
Yeah, man. Sorry. Uh, erase.
Mm-hmm. And are you solving for y prime here?
Yeah.
Okay.
But would it just be zero? Low the low times derivative? Oh, that'd be 6.
Okay, so you found y prime, 3x 2y. Good. Take the second derivative now.
Wait, so it'd be 2y prime. Should be
Okay,
3.
so
It'd just be 3x.
okay, let me stop you real fast. Let me make
Yeah.
a little more room because you're going to run out of room fast.
Well, I'm nearly done. I was just trying to like combine steps.
Okay, so tell me what you're doing here.
So you got y prime equals 3 over 2. 3x over 2y,
Mm-hmm.
right?
And you're using what now?
And I'm using the quotient rule to do like 2y squared and then can okay. Yeah, 3 derivative of the top times bottom minus derivative of the bottom times top. Derivative
Down below.
of the bottom is 2y prime. So multiply, we already have y prime, so multiply y prime by 2. So it's just 3x over y.
Okay, so take it and drop it in. And then you can solve, right?
Yeah.
Okay, let's go do that here together. So you have 2 times y prime. That's going to get you your 3x over y.
Over y. Yeah.
And then we can go ahead and simplify it down a little bit more. Why don't you go ahead and do that? Keep going.
Hold on, let me clear my screen because it's weird. I don't know what you really hold on.
Is that 9x or is that 9x squared?
Yeah, 9x. Yeah.
Okay.
Yeah, that's yeah.
Let's go back with the problem stated again. So remember, we're looking at this problem right here.
Yeah.
What else could you do to simplify it?
I guess look for wait, no. I don't know, separate into 2 terms or something like that.
Look at your equation. Think of equations as like a conversion factor. And if I see it, I might want to use it somewhere.
Oh, well, that's weird.
Where do you see it at?
It just goes into that twice, that top part twice.
Yeah. Let's factor out a 3.
Oh, yeah. Wait, yeah. So,
do you see it now?
Yeah, so, 3 times. I mean, yeah, but what would that do?
That makes it -5.
Oh,
so
that's cool.
See how you can use equations, how you can simplify them down, make it a little bit easier. And sometimes this is exactly what you want to do. Sometimes it's not what you want to do. You just kind of want to see what's going to happen. And one of the conversion factors or the equations you're going to use on a regular basis is the Pythagorean theorem. And we talked about this before, how you use Pythagorean theorem as means of converting a difference of squares. But you can do things like this, and it's very, very useful to simplify it down to get it to a more manageable form. Now, what I want to do is go back up here. And you were taking the derivative. And when you did so, what did you use? Describe the process.
So like the derivative?
Okay. So when you took the derivative here to find y prime, how'd you do it? What was your process again?
Just see, yeah.
You hammered away at it to find the first derivative, right? Because to find the second derivative, you got to first find the first derivative.
Yeah.
Maybe. Now, from here, look what you did. You solve for y prime. And then from the y prime, you took the second derivative.
Yeah.
Without realizing it, you locked yourself into a certain mindset to find the second derivative. See, I have to find the second derivative. And how I do it, well, it's kind of a matter of opinion. I don't have to take and solve for y prime. Because Samuel, what if I couldn't solve for y prime? What would I do then? It's like up here, how am I going to solve for y to find the first derivative? Well, I can't. So what am I going to do then? Well, I don't necessarily, oops, I shoe zero there. I don't necessarily have to solve for y prime. I could just go ahead and take the derivative again, could I not?
Yeah, I mean the
And then I can apply what rule?
uh
Product rule.
oh wait, huh? Wait, but like
Because it's a product. See, I have a y times a y prime. I
yeah,
don't have to use a quotient rule. And
yeah,
I'll get to exactly the same thing in the end. So working a problem one way and then work it another way, that's a very, very useful skill set, especially when you're on an exam and you're making a mistake on something and you can't figure out where your mistake is.
yeah,
This can really help you out. Now, I know what y prime is. I already found it. So now I can
yeah.
take it and drop it in and I can solve for y double prime and I'll get exactly the same thing in the end. So I
Okay.
can lock myself into doing the quotient rule or I can explore and apply the product rule. Choice is yours, but sometimes it's useful to go
Yeah.
this route. Sometimes it's useful to go this route. So how do you know which route to go? Well, it's a little bit of time and experience. And the more problems you work on, the better the feel you're going to get as to which way you want to go with this. But let me stop here and see if you have any questions on this problem.
Um. Yeah. No, I think it makes sense. Just the other way of doing it. Yeah.
Mhm.
That. Yeah.
Good, good. Okay. Well, let me give you this problem. We were talking about this beforehand, but let's kind of hammer it out a little more now. Suppose I want to take the derivative of my arc sine. What is it?
Um. Wouldn't it be like I got a derivative of well, no, just be 1 over square root 1 minus x squared.
Okay. Why?
I remember. I think it's like you got a triangle or
Mm-hmm.
something, and arc sine would be. Oh wait, yeah. You need the inverse thing, but
Talking
so
about this inverse. What's an inverse for a function? Or what's the inverse for sine?
uh just arc sine.
What is
Right.
it? What's it do? How's it defined?
It's like you instead of finding this with these, you find these with this.
Okay.
Okay, that's not a good explanation.
For
Like
a function to be invertible, what does that mean?
it like basically x y gives you x, putting a y gives you x, and putting an x gives you y. Or
Let's say
yeah,
if I had y equals x squared,
yeah,
and let's say if y equals 4,
yeah.
what's x?
Um, x would just be 2,
Sorry. So sorry. X is
2 or
negative
negative 2,
2. That's what I
2
was
or
thinking. So here's the problem, Samuel.
yeah.
This function is not invertible. See, to be invertible means you can reverse what you did. If I say y equals 4, information has been lost. You cannot reverse what you did to get to 4. So what is it about the function x squared that makes it not invertible?
It's just that if you flipped it on y equals x, then it wouldn't be then it wouldn't pass the vertical line test.
You went
It
past the
doesn't
vertical line
it
test.
doesn't pass the horizontal line test or whatever.
Right. So a function is not invertible if it doesn't pass the horizontal line test where it crosses the graph at least twice here. Okay, so this is not invertible. What does the graph of sine look like?
Uh the graph of sine looks like that.
This.
Yeah. So it doesn't pass the horizontal line test. So you
That's
gotta
right.
pick a section of it to you gotta pick this section of it to do.
Perfect. And remember, the section that we typically pick is from here to here,
So negative pi to pi.
not negative pi, but negative
Wait,
pi over 2
power. Oh, wait.
to
Yeah. Okay.
pi over 2. Those are the restrictions that we typically place. Otherwise, sorry. So very sorry. It's not invertible. So whenever you're talking about the inverse sine, that's what's in the background. Samuel, this is what's implied. It's
Yep.
implicit. So theta has to go between pi over 2 and negative pi over 2. Now, in terms of the unit circle, that means you're really looking at quadrants 1 and 4.
Yep.
Now, if I have my sine and theta, and let's say if it equals x, and if I was to take the arc sine, the inverse sine that is, and recall again that I can write the arc sine using this notation, or I can just spell it all out.
Yep.
And remember, do not make the mistake to say the arc sine this is not this. That's a common mistake, and they do put these things on exams sometimes to see if people are paying attention. Well, here's my question. If I want to find a derivative for the arc sine, this over here might be a little bit challenging.
Yep.
But I can do it over here. Because I know what the derivative for sine is. What is it?
It's just derivative of sine is just cosine.
That's right. But what you gave me without realizing it, you gave me the derivative for sine of x.
Yeah. Yeah.
So what if I was going to change that function up right there and say sine of f of x?
Oh,
What's the derivative now?
cosine f of x times f prime of x.
That's right. But Samuel, I got another problem. I got a function right here, or do I? What is that theta?
Um, it's just an angle.
It's an angle. Well, what happens as x changes? Does my angle
X
change?
in the arcs when you yeah, it does,
Absolutely doesn't. Because
But
sine again, you can think as being opposite over hypotenuse.
yeah.
Hypotenuse is 1. So if my height altitude here, my triangle changes, oh yeah, that angle is going to change. So what does that then tell you about the relationships between theta and x?
um they are directly proportional, or they're
Mm,
proportional.
okay. Yeah, I guess you can say it like that.
Can I get a charger real quick?
Go right ahead. All right. So what I'm kind of getting at here is there is a relationship between your function. There is this kind of relationship directly proportional, proportional, inversely proportional. That's not really what we're hinting at here. But theta is a function in terms of x right there. So whenever I take the derivative, I got to apply the chain rule as we're talking about over here. But when I take the derivative of theta is a function in terms of x, which is being implied. So I have to say theta prime. Just like I'm saying when I take the derivative of y squared, I have to say y prime when I tack it on the end instead of just saying 2y. Now, from here, the derivative for x is 1. And what I'm trying to do is I'm trying to solve for theta prime because what really is theta? It's arc sine. Remember, an inverse trig function is nothing more than an angle. So what I want to do from here is I solve for theta prime. Over cosine theta. And here's where I can use my triangle again. I know that sine theta, sine's going to be opposite over hypotenuse. With the adjacency side, use the Pythagorean theorem, it's 1 minus x squared. And cosine is adjacency over hypotenuse. And that's why the arc sine is 1 over the square root of 1 minus x squared. Notice how we had to use different ideas and kind of put them all together. Chain rule, implicit differentiation. And this idea of what does it mean to be an inverse? See, Samuel, a lot of students, they overlook this fact and you just kind of rush right into it. But if you rush right into a calculation, there may come a time which you might need to actually dig deeper and see what are the fine details, the fine print that allows you to do a certain calculation. Because sometimes it may or may not work out the way you think.
Oh, wait, was that muted just now?
Mm-hmm.
Oh, sorry. Yeah. Okay.
Now, what I'm going to do is I'm going to give you this problem now. Ask, what is the derivative of arctangent?
Uh,
And
well,
can you do something similar to what we just did?
Yeah, you do the same thing. It's like, you got.
Take it away.
So make this x, make this right. Yeah. This would be x plus x squared plus 1 squared. Wait. Right? Yeah, x. Wait.
But how'd you get that?
Um,
Use your definition. See, you need to write it out over here that the tangent of theta is x.
Yeah, and then
if you like.
Okay, and then arctan of x is theta.
And are you sure about this?
No, that's wrong.
Okay.
It's square root x squared plus 1. So basically, if we do it like we just did, it just become wait, hold on. What would that be? It should be cotangent of negative. Wait, would it be negative? No.
Don't go cotangent.
What?
Go ahead and scroll back up. What did we do up here?
We just oh wait, yeah, sorry. So yeah, wouldn't the derivative of tangent just be cotangent theta times theta prime?
Mm-mm.
No. Wait.
What actually is tangent?
Sine theta over cosine theta.
And what rule can you use then? It's a quotient.
Quotient. Oh, maybe, yeah, okay. Wait, but yeah, I have to use quotient. No, never mind. Sorry. So it's just gonna be
Now, this is going to be a little confusing right here with the theta that we have up here. Let's
yeah.
just look at it in terms of x here for a second. Otherwise, it's going to cause a problem. Okay. So you're going to have your derivative up top, which is cosine. Derivative for sine is going to be a cosine function down below, and then subtract it off what?
Subtracted sine squared.
Okay, so you have your function up top times your down below. Derivative down below is going to be negative sine. So that's why we have a positive. So we're going to have
Wait.
sine squared x.
And then I remember now. So, and then you could just basically turn it into 1 plus sine squared x over cosine x.
And what's that become?
Tangent squared of x. Oh shoot! What did I do? Good. Wait, my annotate's not working.
Okay, you tried now?
Yeah. Okay.
Nope, that's not what you want to do at all.
Oh,
what's cosine squared plus sine squared?
Oh wait, it's just 1. So it's just gonna be 1 over cosine squared.
That's right. You just want to apply the Pythagorean theorem. And what's 1 over cosine?
1 over cosine, it would just be secant
Perfect.
squared, yeah.
Okay,
And then
so the derivative for tangent is not cotangent. What is it?
it's secant squared of x.
Exactly. All right, so let's go ahead and erase all this down below, and let's go back to the problem at hand.
Oh,
okay, let's go back to where we had up here. Take it away. You see how to figure out the derivative of the arctangent, but to do that, we're taking it from the tangent perspective.
Secant squared would just be this over, just the hypotenuse, which would be x squared plus 1.
Wait, Samuel.
Wait.
The derivative for tangent theta is secant squared.
Oh, secant squared theta times theta prime.
Good. And what about the other side?
Equals 1.
1. Okay, so don't jump into it here. I know you're pretty eager, but we want to show over steps. We're trying to solve for theta prime because that's going to be our arctangent prime since theta equals the arctangent. What do I do next?
It just becomes secant theta again, right?
What's 1 over secant?
No, I mean, sorry, cosine squared theta again.
Mm-hmm.
And so, and then you just do it from here. It become wait, yeah. No, wait, just 1. Yeah, wait, what am I doing? 1 over x squared plus 1. But it wouldn't be that because it'd just be it'd just be like that. I think.
Well, be certain about it.
Because there's no you don't derive it anymore. If you're just looking at it as like an angle, then it's just gonna be like that.
Okay, so your derivative for the arctangent is 1 over x squared plus 1.
Yeah.
So these are two identities. Yes, you do need to make sure you do know what they are.
It's like
But if you can
So,
take it deeper to what we did,
uh,
it's gonna help you
hello,
out immensely.
hello.
Can you hear me okay?
Yeah, my audio just like cut out like kind of weird, just like kind of bad. Just okay, just say after I.
Not a problem. So what you need to make sure you know is you must know the derivative for your arc sine.
Okay.
And you must know the derivative for arctangent. Now,
All right.
what they're going to do in the class is they're going to say, well, there's four other ones. They're for arc cosine, they're for arc cotangent, they're for arc secant. Those honestly, Samuel, they don't come up that much to make it worth your while. Now, it is useful, and they're probably going to put it on an exam or two, but you're really not going to use them that much in a calculus class.
So it'd be more of like an extra credit question. Like,
That's usually how I put it when I'm using it. But
yeah.
if I'm going to have a derivative for the arc cosine, can you guess what this one might be? Or can you think what
The
this one is?
arc cosine. Oh yeah, so I I think it would be
It's just
it
negative
has
up
something
here.
to do with this. So yeah, okay, yeah, okay.
And you're never going to really use the arc cosine. Well, I won't say never, but more than likely not. The
Okay.
other one that's kind of pops up ever so often, that's probably, yeah, you might want to know it for an exam, is your arc secant, its derivative.
Oh,
And this one gets a little bit more interesting.
the thing, can you
That's what it is right there.
okay.
But the main two, the big two that you're going to see on a regular basis are these two up here.
All right.
So I would just probably make sure you know the other four for me for an exam if you needed to. They're going to have a very similar feel to what we have, like with the arc sine, the arc cosine, and how it flips. And then just kind of go from that perspective.
All right.
Good. Any questions on that?
No, not that I could think of.
Okay. Well, let me throw you a few problems here. Let's take it back to these up here.
Okay. Okay.
And what I want you to do is see if you can find y prime for me. How fast can you do it?
I'd probably want to use natural log, seeing as there's like a
I wouldn't. There's a plus sign right there.
oh yeah. Yeah, but it makes it so no wait. No, I think it could still work because you just get actually no that'd be but then okay. Okay, then I'll just have to implicitly differentiate then. It's gonna be like messy. Is there supposed to be like a good way to do it? Like
No, no,
a
no. Let's see if we can find something out here.
um
Now, see if you maybe write a little bit smaller because you're going to run out of room fast.
sorry. Okay, maybe start by factoring out y squared. Is that gonna help? I don't think so.
Okay. I like how you're thinking there, trying something new, trying something different. That's you're thinking like a scientist now. Okay. So if it doesn't work, go back and try something else.
Yeah. Um, um, natural log
No, naturally, not going
wouldn't
to work because the plus sign
work.
there, that's really
Well,
causing a bit of a snag.
you could do like -2 natural log y.
Why don't you just use straight up product rule?
Yeah, yeah,
2x y
that's what I
cubed,
was that's what I was
3
doing, and then I was thinking what else I could do.
y prime.
Actually, it's not going to be that bad.
Not too bad in this case.
So it'd just be E. Wait. Oh yeah. I have to use product rule again. Uh. Wait. Wait. Uh. Oh, and then I could like. I see. I could like put this like move this over like divide this by that. Right. And then
Like terms.
wait. But then that wouldn't work because you still got this.
Yeah. Distribute and collect like terms.
But why would I want to distribute if
Because
oh
you
yeah,
can unlock the
because
y prime.
yeah. Uh so just isolating them all to one. What would it be? It's plus, right? No, wait, no, just there isn't anything here. Just like that. Wow, where's my pen? Um so then it would be y prime for y plus 3x squared y squared plus x e x y equals
Minus
minus. Oh yeah.
y
Oh
cubed.
wait. Yeah. Minus y cube and then plus y. Yeah, and then you just divide these, and then
Mm-hmm.
it's running. Yeah, I shouldn't have wrote that big.
Okay. So we got there. It took a little time though, right?
Yeah.
Okay. Let me see if I can take a little snapshot of that.
Okay. Clear my screen. Oh, okay. Yeah.
Okay. And let's say if I was going to give you this one, right here. How would you find y prime?
Oh, that's. Oh wait, no, that wouldn't be that bad. It'd just be uh negative sign xy times.
Missing something.
Then um, I am.
Mm-hmm.
Thought I had all the
How'd you get that?
derivative of y squared, and then I had yeah. So I put the
But everywhere you encounter y, you take the derivative.
I did put y prime up.
There's y prime. Good.
Okay.
Okay. Now we can definitely distribute the y primes out and solve from there. Let's forgo that here for a second. And let me ask you this question. What if I start getting a little more creative?
Huh?
What if I had this one?
Um,
You said we took it to the next level.
yeah, this is still just applying all this, right? Not like sorry, I can't erase it anymore for some reason. Yeah. Um, yeah, this is just gonna be like applying it, just like yeah. There's got to be a way to like do it better.
There's
I
got to be a
think.
way, doesn't there?
Yeah.
So, is there a way to do it a little bit better? Yes, there is. Now, this is something they usually don't teach you until you get to a higher level calculus. But let me kind of give you the quick rundown of how you can find implicit or how you can get the y prime implicitly really, really fast. Uh, just make sure you kind of hold this lock and key. Don't let anyone know about this secret right here. But this can kind of give you a nice competitive edge. So let's just kind of look at a nice little example that we can figure out real fast. Let's say we have x squared, and let's say we have y cubed, and let's say this equals xy. Let's say 2 or something.
Yeah.
Now, what I want to do is I want to get everything from one side to the other side. So I'm going to make sure that one of the sides zeroes out like this.
Yeah.
And then what I'm going to do from here is I'm going to take our differentiation, I'm going to tweak it a little bit. And this is something that's called partial derivatives. Now, this is something that's not really taught at this level. It was taught at the next level, but this will give you a fast way to do these problems here, Samuel. Now, here's how it works when I'm doing partial derivatives as opposed to just taking our derivatives. It's a little bit different. If I'm taking the derivative, I want to do it once in terms of x, then I'm going to do it in terms of y. See, x is going to be the variable that's changing. Down here, y is the variable that's changing. So if x changes, what does it mean in terms of y?
Um.
It's not. So you
Yeah.
treat it like a constant. And down here, we see that y is changing. So if y is changing, what's that say about x?
What x isn't wait.
It's not.
So
So you treat it
so
as a constant.
so d dx and dy dx would be different things. Like
Exactly.
technically, okay.
One you're doing in terms of x, the other one you're doing in terms of y. Good.
It's just like it's just like you're not it's really not it's not you could use it if it's like a if it's explicit differentiation because y doesn't wouldn't change anyway.
Yeah, there's some similarities here. Now,
Okay.
you learn about really what's going on within maybe a year or two from where you're at. We're just kind of dipping our toe into it to show you how you can do this a little bit faster so you're better on the exams.
All right.
Okay, so just point in case real fast. If I have 2x and if I was going to have, let's say cube, so you can see what's going on a little better. And if I had y, x to the third and say y squared. If I take and oftentimes you write a little hook symbol, but I won't worry about it. But if I take it in terms of x, I'm going to treat all the y's as constant. So what I have here is 6x squared, treat y as constant. And with constants, you leave it alone. And then do it in terms of y. And then x is constant. Derivative of constant is 0.
Just
So there's no y's there. X is constant. Leave it alone. 2y. Now, from here, if I was going to go about this the typical way, I would have 2x, 3, y squared, y prime, product rule, 2 derivative for x is 1, y, and then I'll have 2x, y prime, collect all my y primes, move things over to their side, and then solve for y prime. Something maybe a bit like this. Now,
Wait.
there's something that's going on here. What's
Yeah.
going on?
Um. Um. This is okay.
Is it a little bit too much for you?
No, no. I think it's just
We
Sorry, I
are
think my
really
sc- my
reaching
my
up, not running the ladder
my, my,
pretty high here.
my screen froze in the middle of it, so
Oh,
like I like it just jumped up out a bunch, and I just so could you just explain it like one more time, just from here?
okay. Let's go back a little bit. Got a few minutes here. So I want to take let's just do it like we typically have done it. We'll take the derivative. So
Yeah.
what we'll have here is we'll have 2x derivative. We'll have 3y squared, y prime, product
Yeah.
rule, because I spy a product.
Yeah.
2y, 2x, y prime. And if I'm trying to solve
Okay.
for y prime, I better collect my y primes, shouldn't I?
Yeah.
Absolutely. Pull it to the other side. Pull things over to the other side. And then from here, solve. Right there.
Yeah. Okay.
Okay.
Yeah, I was just trying to find how you integrated like the from the right side to the left side. I was kind of confused by that. Um,
Okay. Now, here's what I'm going to do. I'm going to look at this problem here, and I'm going to do it in this new way that I'm showing you. Now, the
Okay.
first thing is I want to make sure that there is a 0 on the other side. Otherwise, I'm in big trouble. And I'm just going to call this whole entire side over here, I'm just going to call it F. So you can just kind of have something to hold on to.
All right.
So I'm going to take the partial in terms of X. And then when I do that, remember, X is changing, Y is not.
All right.
Y is constant. And when I do this partial differentiation approach, I'm not tacking on Y primes.
Yeah.
Okay, so Y is changing, X is not. Treat it as a constant. Just like that.
All right.
Now, Sam, I want you to just look at this for a second. What do you see?
Oh, yeah. It's just the d dx over d dy.
Pretty
Yeah.
close, isn't it? So,
Yeah, almost negative d dx over d dy.
negative. That's it right there. So this approach, I'm going to call this now, let's say f sub x, and let's just call this f sub y. This is how you can very, very, very quickly find the y prime implicitly. Now, they don't teach you this, once again, for years to come, but now you know the inside scoop, how you can find this real fast. And the
Oh.
steps again is you have to, no ifs, ands, buts about it. You got to get that 0 on the other side. Then once you have it like this, form your ratio, and you're pretty much done really fast. Okay, so what I want you to do is I want you to kind of use this partial differentiation idea that we just learned about. go back to these past problems. Let's see if we can find them up here again. And I want you to rework some of them now.
All right.
Okay, so here they are. So use that approach and rework these problems the new way and the old way and see if you get the same thing.
All right.
Okay, how you feeling about all that?
I'm feeling all right. Could I get maybe get a screenshot of like just now the example for partial differentiation? Because like I was doing my homework by through the YouTube video. I was just looking at the problems from the YouTube video.
Mhm.
So could I real quick just can you real quick just scroll down to the partial differentiation?
Let's go back to it.
Okay,
Yep, can you grab a screenshot?
got it. Thanks.
All right, so let's go back up here. So you're ready to go in these new problems.
All right.
Okay, now the next thing that we're going to look at is we're going to look at some more applications in terms of implicit differentiation and what that all entails.
Okay.
But once again, try this new way and see how fast it goes and how you can give yourself the competitive edge.
Okay.
All right. Well, Sam, you have a great day and I'll see you next week.
Okay.
All right. Take care.
Thank you, Mr. James. Bye.
Bye.
I hope that today's lesson was a positive and an encouraging learning experience, and that you have a better understanding of how to solve these problems. Be sure to set some time there today and throughout the week to review these concepts, to rework these examples so that you're better prepared for the next lesson. If you need anything, just let me know. You're always welcome to send me an email or to stop by during office hours. Until next time, keep up the good work and have a great day.